So, right. So I will be returning your grade exams next week. So hopefully things went well. So the next problem set is available, and it's due a week from Friday. After that, there will be one more assignment, which will be only the extra credit. Okay? All right. So we'll hopefully then have enough time for everyone to get ready and review for the final exam. So for some of you, just now, we were talking amongst ourselves about this timing and whether this is actually a good day, given that there is another exam happening on Monday. I see no reason necessarily to have both the final exams on the same day. I'm fine to change this. It can be on Tuesday, except I won't be here because I have to have some minor surgery on Tuesday. So, does anyone have a thought or a preference?
I would prefer Tuesday.
Tuesday, yeah, I agree. I think there's no reason to have both. Yeah.
This is locked in on Monday, right? He wasn't just saying, I think it's gonna be on Monday.
He did come.
That's the thing, he just kind of threw it on, it's like, oh, it'll probably be early in the week, so.
I'll talk. Why don't have to settle it? The only thing, since it's fine, let's work it out. We'll find out when. This is in what course is in math?
Oh,
yeah. He's having a final.
You should tell that to him.
It sounded unmeasured last I checked.
He told us that if we don't have a final, he did good in class exercises. I hope we can do it.
All right. Yeah, that's right. Yeah. Okay. Anyway, all right. TBT.
Bullet point, final exam. No, I will not elaborate further.
All right. Very good then. All right. We'll look at that. Okay. All right. Very good. So, let's see. So, what we have discussed in the course so far is we've talked about fields arising from sources. And we've done this in two contexts. We've done this in the context of statics, right? The case where the charge density is constant and the current was a steady flow. So this context is both electro and magnetostatics. Yeah.
Was problem set 10 the extra credit one, or?
Yeah.
Okay.
Yeah.
All right, cool.
This is not extra credit.
Okay.
This will be on the final.
The extra credit?
All right. So back to our originally scheduled program. We talked about field arises from sources in electromagnetostatics, and we talked about quasi-statics as well. Where we included the fact that you can have a curling E to a changing B, but we, sort of ignored the displacement current and the full description of the field that way, and we gave some conditions that we'll review under which the quasi-static approximation was appropriate. So that's one thing we studied a lot of. And then in the recent weeks, months, we've talked about electromagnetic waves. And those electromagnetic waves are just there. And we didn't really talk about the source of electromagnetic waves, how electromagnetic waves are generated from the sources, okay? So that's what we need to do next, and that's the problem of electromagnetic radiation. Which is our subject for the next couple of weeks, okay? All right, so before we get to this, let's sort of review how we solve this problem kind of formally, okay? So in the case of statics, Maxwell's equations have the following form. And if we wanted to solve for the electric and magnetic field, given a certain charge density or current density, the easiest way for us to do that was to first write the equations for the electrostatic and vector potential, and then from that we can get the fields, right? So the two equations that don't involve the sources define the potential, okay? So the fact that the curl of D in electrostatic was 0 told us that we can write E as the gradient of a scalar, and by convention we write it as minus the gradient of phi in the relationship to potential energy.
Are we going to be doing all of our, at least preliminary derivation for radiation with microscopic Maxwells?
Yes, everything is in the microscopic case to start. Yeah, yeah. And similarly, this equation told us that the magnetic field can be written as the curl of another vector, okay? As we may or may not remember, every field can always be written as a part that is the gradient of a scalar and the curl of a vector, a part that has 0 divergence, so it's and a 0, or what its curl and divergence are, determine what the fields are, okay? Now, the fact that this is the curl of a potential and there's no part that has to do with the gradient tells us that we have gauge invariance. Which is to say that the divergence of A is arbitrary. There's nothing physical about the part of the vector potential that is its divergence. It in no way affects anything observable, okay? So we can choose the divergence of A any way we'd like. Hmm?
Is that specifically all that's required for it to be gauge invariant?
To say that it's gauge invariant means that we can shift A in a particular way without in any way affecting the physics. That's what we mean by gauge invariance.
Okay.
In this particular case, what it means is this, okay? And that is to say, I can shift the divergence of A by making a gauge transformation that A goes to, I can add to it something which is the gradient of a scalar, and this tells me that A goes, that the divergence of A goes to what it was originally plus the Laplacian of chi, and I can choose this any way I like without in any way affecting the physics. Okay? So I can shift A in this way. This is what's known as gauge transformation without changing Maxwell's equations. Okay? Now, for statics, we said if we're going to choose this in an arbitrary way, we might as well choose is to just get rid of the divergence of A. Don't drag it away around the part that's that, because we can choose it anyway, like just get rid of it, okay? So with this definition of the potentials and the relationships of the electric and the magnetic fields, and this particular choice of the gauge, we then get equations of motion, as you like, or equations for the scalar and vector potential that are from the other two Maxwell's equations that have the sources in them. So if I look at del dot E, that is equal to del dot minus the gradient, which is minus the Laplacian of the scalar potential, or the electrostatic potential, which is equal to 4 pi chi, right? So we had del squared phi is minus 4 pi rho, which is Poisson's equation. Okay. Similarly, Ampere's law now tells us that the curl of the curl of A, which is equal to, what's our favorite
Gradient
vector?
of the divergence minus the
Gradient.
Laplacian.
Gradient of the divergence minus the Laplacian is equal to 4 pi over c times the current. Okay? And this is 0 by this choice of gauge. We don't have this extra term there. Okay? So what we saw many months ago now is that the scalar potential and every Cartesian component of the vector potential satisfies the Poisson equation. So if we can solve the Poisson equation, then we can solve for the potentials as a function of the sources. And once we have that, we have the fields through one of the legs of Steve, which tells us how to relate the potentials to the fields. Okay? Now, how do we solve Poisson's equation? Green's function, right? So the solution to this is to say we can say that, so this, for example, tells us that the potential at some observation point is going to be what we sometimes call in differential equations the homogeneous solution and the particular solution. Okay? The homogeneous solution is something, so this tells me that this I can choose, the homogeneous solution is a solution that satisfies del squared is equal to 0, which is Laplace's equation, and I can choose the homogeneous solution any way I like to satisfy the boundary conditions. Okay, that was something we did. Whereas this satisfies this with the boundary conditions that it goes to 0 at infinity, okay? So if we don't have any boundaries to worry about, the particular solution we can find by the Green's function method. And the Green's function method, again, is just about the principle of superposition. If I know what the solution is for a point charge, then I know it for any distribution, because I can make any distribution out of the superposition of point charges. Okay? Yeah.
What was your note about boundary conditions?
Well, what I'm saying here is generally the homogeneous solution is chosen to match
Okay.
whatever boundary conditions you have. If there are no boundaries, then we take the field to be zero at infinity.
Okay.
So the particular solution we get by the Green's function, and the Green's function is just the solution, say, for the potential for a point charge. Okay? So, the Green's function is the potential at x given a point charge at x prime. And so the charge density associated with a unit point charge at x prime is a three-dimensional delta function localized at x prime. Okay, so this is rho at x given a point charge with unit magnitude at x prime. Okay, the charge density is zero everywhere except at x prime, where it's infinitely concentrated. Okay, so if we know this, we know the solution, because since rho, a general rho at x, can be written as weighting point charges localized at x prime by the charge at x prime, then the potential we get by just convolving with the Green's function. Okay, that was the Green's function method, just to review it. So, we can solve for the Green's function in principle using Fourier transforms, going to the Fourier domain, inverse Fourier transform. And we have, for the Poisson equation, of course, we know the answer to that. The answer to that is the charge, which is 1 over the distance between the point of observation. That is the Green's function, which is just the familiar solution to the Coulomb law. It's what the potential is. Given a point charge at x prime, observer, the potential is 1 over the distance, right? But we could do something very formal and do a Fourier transform and invert it. We get that, okay? And so this tells us that the potential which is just adding up the electrostatic potentials for every point charge at x prime of this magnitude, right? And similarly, for the, since A satisfies the same equation, but for each Cartesian component of the current, this tells me that the vector potential for this choice of gauge is equal to the integral over x prime, the current at x prime over c x minus x prime. Okay, I just did a review of the solution to Maxwell's equations in statics. Okay, done very formally. All right. So now, with that said, let us return to this same problem, but now with including not just in statics, but the full Maxwell's equations in dynamics, and let's solve them. And we're going to solve it exactly the same way. Okay? So now we have Maxwell's equations, including time dependence in its full generality, which now tells us that the curl of E is equal to minus 1 over C dB dt. That's Faraday's law. The divergence of B is unchanged, and the curl of B has now the displacement current in addition to, and as Don would remind us, we're talking about the microscopic Max's equations here, okay? All right, how are we going to solve this?
What are we trying to find?
We want to find E and B as a function of the current. And which, we just did this for statics. Once we have the potentials, we have E is the gradient of that gives us Coulomb's law, and B is the curl of that gives us the Biot-Savart law.
Solve for the wave equation.
Well, we can, but that's going to be very complicated. I just said we're going to solve this in exactly the same way as we did here. So what do we need to do?
Maybe I'm missing something,
Yeah.
but can we can't really write the electric field in terms of a scalar anymore because it has a curl to it? Is that?
Well, yeah, that's exactly the point. So what we need to do is we need to find the potentials now in statics. And the point that you made is exactly the right one. We no longer have that this is just simply the gradient. This is still true. So it is still true regardless of whether I'm in statics or, so let me say, trying to say too many things at one time. One thing, it is still the case that the fact that the divergence is 0 implies that this is the curl of a vector. That is for sure true. But only in statics did we have that the field was irrotational. It had a curl of 0, and because its curl was 0, it meant that it was always the gradient of a scalar field, okay? But the curl of E is no longer 0. However, if we plug in for the curl of A here, we get that the curl of V is equal to the curl of that, which means that the combination is 0. So what does that tell me? Well, that's wrong. This is right. What does that tell me?
We can make a scalar potential for that quantity.
That's right. That means that this whole combination is irrotation. Its curl is 0. Therefore, this combination is now the gradient of a scalar. So in full electrodynamics, it is now the case that the vector potential determines not only B, but E as well. So E is now equal to minus 1 over C dA dt minus the gradient of phi. Okay. So this is important new realization that we have a situation now where the vector potential takes on a more important role when we're thinking about dynamics. Yes?
So you said this is a more general version of Maxwell's equation. I guess that would mean we could also use this for statics. It would just be that dA dt is 0.
Yeah. Indeed. All right. Now, there's still gauge invariance because it's still the case that the divergence of A plays no role here, okay? So the divergence of A is still arbitrary. But now we have to think about what happens in terms of what do we have to do to the potentials to do a gauge transformation. Yeah.
I don't exactly see how the divergence of A is still meaningless here, because we had A in E, like just the A vector.
Right, but if I always can write A as a part that is transverse and a part that is longitudinal. The transverse part has 0 divergence, and the longitudinal part has 0 curl. Okay, this was we had from Helmholtz theorem that we studied at the very beginning of the semester. Okay, so the part here, what we see is that the curl of A comes in over here, but if I look at the divergence of A, I can always shift it by shifting what the potential is without changing in any way what E and B are. So let's look at this specific to see how this divergence comes in. So let's think about what a gauge transformation is. So let's say whatever A is, I transform it and add to it something which shifts its divergence, okay? This thing has a finite divergence, and that will shift the divergence, okay? In this situation, B is unchanged, because the curl of this is 0. Yeah, done.
We have to add chi del t.
I'm not there yet. So I just said one thing at a time. Let's just give me a moment. So if I do this, I don't change B. But I will change E unless I also shift phi, okay? So when I do this, if I simultaneously shift phi, and let's see how we would have to shift it. We would have to shift it, so let's say I make this change alone. That would tell me that E would go to minus 1 over c dA dt minus 1 over c d by dt of the gradient of chi minus phi. And that would give me an extra piece of E, which I don't want. I want to keep E the same, which means I have to simultaneously shift phi in a gauge transformation. How should I do it?
You should also shift by chi.
Exactly, and how should I do it? Right. If I add that to that, then I cancel these guys, and E goes to E. Okay? Yeah.
So, in our situation, you can shift our feed because we can choose where ground is.
It's not really about ground now, because it's also about, as we'll see, your favorite thing, the retarded time. This is not about ground anymore. This is about a dynamical field. And how I apportion to what part I call the scalar potential and what part I call the vector potential is arbitrary. I can rearrange them. I can shift A and phi in particular ways by doing this transformation through this scalar field. If I add to A this and subtract from phi that, I in no way change E or B.
Same things.
And so the forces on the charges are the same, that's all that matters, okay? And so A and phi can be reapportioned in different ways. What I see from this is that I can shift, what this does is it shifts the divergence of A. It doesn't shift the curl, but it does shift the divergence. And so what I'm saying is I can add anything I like to divergence and not affect anything. That's really the point, okay? So this is what's known as a gauge transformation. And I can choose thus the divergence of A any way I like. That can be convenience, okay? There are two choices that one often takes. Okay? I can again set the gradient, the divergence of A to be 0. That's a perfectly good choice. For reasons that will become clear someday, maybe today, maybe on Tuesday. This is known as the Coulomb gauge. Okay. Another choice, let me make sure I get the signs right there because I can't remember them. Is to choose the divergence so that its sum with this is 0. And this is known as the Lorentz gauge, which will become clearer someday. I could just say briefly that the Lorentz gauge is the gauge which is the same in any inertial reference frame. The Coulomb gauge is not its reference frame dependent. Omar, you had a question first, and then Ben.
So we say that gauge choice does not matter, or it is artificial in a way, but when we take these gauges, we have non-relativistic case and relativistic case. So how do we interpret the difference?
Well, I wouldn't say that they're relativistic cases or not. What I would say is there are gauges that are frame dependent or not, okay? So Maxwell's equations are relativistic, okay? Maxwell's equations are correct when we include relativity, okay? And so we're not making any gauge choice that is only true for non-relativistically moving charges or not. The choice of gauge, as I say, as long we can shift around A and phi any way we like without in any way affecting the solution. But we have to remember what gauge we picked so that when we write down what the fields are, we can ensure that we've done it correctly, okay? This will hopefully come into better focus when we see the particular application. Yeah, Ben.
Yeah, so my question is, this might be frustrating, but almost identical to Omar's, in that I would thought, gauge choice doesn't matter, but in this case, we have a strictly more general choice than the other.
I wouldn't say it's general, it's specific. There are two different choices. I can choose this, or I can choose this.
You can, in choosing the second one, we can do both dynamics and statics.
No, we can do dynamics here too.
We can?
Yep, and I'll show you how.
Okay.
But you'll have to wait. Yeah, it's a perfectly fine gauge. We're gonna choose this gauge, but give me a week, and we'll understand how this gauge is perfectly fine. It's actually the gauge I always use. We always use this gauge in quantum optics. Yeah.
How come the Coulomb gauge isn't frame independent?
Because A and phi transform into one another when I make a change of, if I go into a boost, right? So hopefully we'll get to that in the last week of class, but as you probably, I hope you learned, what looks like an electric phenomenon in one frame can look like a magnetic phenomenon in another, right? And vice versa. E and B transform into one another, and so do A and phi. But the way that they transform by Lorentz transformation is such that this gauge will always be true in all reference frames, whereas this gauge will not be true in all reference frames, but that doesn't matter, as long as I fix the reference frame.
So I can say the bottom line is when I see the A and phi dynamics.
Yeah,
Then it can be frame dependent,
absolutely.
but when I get the Maxwell's equation using those formulas, I should get large.
Well, I wouldn't say that. E and B are also frame dependent. But the relationship between E and B and rho and J are what they are in some reference frame. Okay? So what looks like charge in one reference frame looks like current in another reference frame. Here's some sitting charge. I'm moving one, but now the charge is moving with respect to me. So when we're writing Maxwell's equations as written, they are in a particular reference frame. Now, as we hopefully will discuss, I can write what's called in manifestly covariant form, very fancy names, manifest covariant. Manifestly covariant form of Maxwell equations, which obviously have the same form in every reference frame. As written, they are with respect to one reference frame, and we can't really see because how E and B, but we'll have to be patient to get there, okay? All right, very good. So with this said, we now can write down, okay, what we did when we did statics, we said, okay, we have the potentials, this is how the fields are related to the potentials. And then the next step was to find the equations of motion for the potentials, and then solve them, which we did using Green's functions, okay? So that's what we're gonna do. We have two more equations left, the ones that involve the sources. We haven't used these yet. So now we just plug it back in. So we have that the divergence of E, which is equal to minus 1 over C d by dt, the divergence of A, minus the Laplacian of phi is equal to 4 pi rho. Okay? But, I'm going to write this. I'm going to choose the Lorentz gauge, just because it's the easiest one to work with. And so this tells me that the divergence of A is equal to minus 1 over C d phi dt. Okay? So when I put that together, what I find is that the Laplacian of phi minus the second derivative with respect to time over c squared of phi as a function of x and t is equal to minus 4 pi rho, which is a function of x and t in some reference frame.
Looks wavy.
Which is the wave equation. It's the wave equation for phi. Okay? Very good. We have Ampere-Maxwell equation. Blah, 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 blah. And E is equal to minus 1 over C dA dt minus. Right? So I plugged in for B, and I plugged in for E. All right? And again, we plug in the Lorentz gauge. That this is equal to minus 1 over C. Right? And so what I find from this equation is that this is the same as this on this side, right? These two things. So this cancels this. And I get, again, that del squared minus 1 over C squared d squared by dt squared A is equal to minus 4 pi over C J. Which is the wave equation. So what we have found in the Lorentz gauge is that A and phi satisfy the wave equation with the source now. It's not a wave equation in vacuum. It's a wave equation with a source. Okay? So now, this is sometimes called the D'Alembert, which I can't spell, sometimes written as box. Okay? So, how are we going to solve that equation? We have a way to use the Green's function, right? Now, again, we can have a homogeneous solution, which is the solution without sources. That could be anything as long as that. But if I think about the particular solution, then the particular solution would be, I would look for the so we have that box, or D'Alembert.
Is it the D'Alembert?
Yeah, okay. Okay, so this is Maxwell's equations for the potentials in the Lorentz gauge. The potentials satisfy the wave equation with sources. And we need to solve for that. And in particular, the Green's function is the solution to the wave equation for a point source of unit magnitude. So we're going to solve this for a point source where the point source is a point in space and in time. Okay? Let us contrast that with what we had over here with statics. For statics, we had the Laplacian, and we had a point source at some particular point in space, x prime, and now we have the wave equation with, instead of the Laplacian, we have the D'Alembert, and this is a point source. So what is this equivalent to? It's like asking the following thing. Suppose I have a point pebble, and I drop it in a pond. It's going to go, and what's going to happen? There are ripples that are going to flow out through the pond. And that's an impulse. It happens at one instant of time, it drops in, and it happens at, if it's a point pebble, it happens at one point. And so once we know what is the radiation generated by a point source that happens at one point in time, we can know what the radiation is from any source that's any function of time and any function of space through the principle of superposition.
When we have Green's functions of multiple variables like that.
Well, we already did. We had it for 3 variables, now they're just 4.
Right. I mean, okay, yeah, and the 3 variable case, it wasn't generally separable, so that
Yeah.
doesn't have to be here. Right?
Yeah. Now, solving this can be done in the same way that one does for this by taking the Fourier transform and so forth. It's in the notes. It's messy, and it involves, I mean, how many of you know, I don't know if this is something that you learned in your undergraduates or in your math methods, the theory of contra-integration and the theory of residues.
It was not that.
We didn't do contour. We did contour.
No.
All right, we'll duke it out another time.
Oh, we did characteristic curves, that was a
Yes.
different thing.
Yeah.
Almost.
But anyway, that's what you need.
This is
okay?
random, bro.
So you need that, and I've heard through the grapevine that you didn't cover that. So anyway, you will learn it another time, okay? So we're gonna take it out of the oven, and the answer is
Oh, that's right, okay. Maybe it's on
Like 5 minutes.
the- Yeah.
so. It looks similar to what we had for statics, but there's an additional delta function. Okay, this is also a function of T and T prime. Pardon me. I did. He's right. I forgot. This is why there are typos in your exam. I don't see them. All right. So interesting. This is for you, Tristan.
Yeah.
So what we notice here is 2 things. Well, we have our same sort of 1/r type potential, but this thing is non-zero only at a particular time, okay? And that is when, let me see if I got the signs right on this. I think I did, but let me just double check this. Yeah, right. So there is, this thing is non-zero only when t prime equals this time, right? And what is that time? It's the retarded time. What does it mean physically?
Travel.
It counts.
So this, what is this time?
Time to travel from X prime to X.
Right.
Speed of c.
So this is the time it takes light to travel between the source at X prime and the point of observation at X. Which makes sense. This is all about causality. all right? This is saying that what the potential is at some point in space, at some time, depends upon what the source was doing at an earlier time. Because it takes time, the time it takes for light to get from the source to the point of observation for me to observe it. Okay? Yeah.
So it makes sense to me that, you know, it would be 0 until the retarded, like.
This is for a point.
Yeah, okay. But the question I'm wondering is that, does this mean it's only non-zero instantaneously?
It is. If I have a point source that's only on for a point, then I'll only see that at a point in time. If I have an extended source that's on for more than an instant of time, then I have to add up all those and I'll see it for the whole extended time.
Which is where it's superposition.
That's right. So this is for a point source at a point in time. And so I only see the potential at one point in time. And that point in time is when these are equal. So we often think about this, so I can think about this, you know, in a kind of space-time diagram, where I can think about this as space. Let's say this is X and Y, forget about Z, I live in flatland, right? And if there is a source that goes off at the origin, then what I get, in the same way that I dropped the pebble, and I would imagine that ripple flowing out circularly around this is a spherical wave that is going out from the origin. This is the Green's function. The Green's function is a spherical wave in the sense that the strength of the wave falls off like 1 over the distance, okay? And in this case, it's just boop, it's 1 plop, and this is
1 over the distance also means like with time, since distance is time dependent.
What's that? Can you repeat the question?
1 over distance.
Yeah.
Also means like with as time increases.
Well, the time dependence is buried in here. We'll see the relationship between the space dependence and the time dependence is buried in here. But the strength at a fixed time, then it would fall off with distance in this way. Yeah.
Can I imagine this physically as something just like an electron popping into existence just for just a second?
That's right.
Okay.
Perfect. I get it. So if I just had, boop, there was an electron or not, it would create this one wave front, a spherical wave that would propagate out.
Okay.
So, given, as we were just saying, the principle of superposition, what this tells me is that, given what we just had over there, this tells me that the scalar potential, I integrate over all sources at all positions and all times, the Green's function times the source. Okay? And if I plug that in, what I find is this is equal to because I can do the integral over t prime, and t prime is only non-zero at this time, I'm left with the following integral. So the only difference that we have compared to what we had in statics, is that the potential I see at my position and time depends on what the source was doing at the retarded time. summed over all possible retarded times depending upon where the sources are. Okay. The same is true for the vector potential. And once I have the scalar and vector potentials, I can find the electric and magnetic fields. Okay? So the retarded time, it's important to remember that the retarded time is a function of x minus x prime, the distance between the point of observation and the source, and the time at this time of the observer.
You mentioned that we have to sum over all the retarded times?
That's right, this is x prime. I'm summing over all x prime. And so the retarded time depends upon where the source was relative to me.
Right, okay, so the T-ret actually has an x prime in there.
It's,
Yeah.
this is important to remember, it depends on x prime, and t. So we often draw this together. Let me think about a space-time diagram where I have one space coordinate and one time coordinate. This is the light cone. This is my forward light cone. This is my backward light cone. For me at the origin. There can be charges moving, okay? Now, the charges move as a function of position in time, and they move as a function of time. And those, they move in some way, they move slower than the speed of light, okay? So, this is what's called the world line of a particle. Could be an electron. Okay? Now what I see at my point of observation is what this particular particle did in the past, and that radiation will travel to me at this later time when it crosses my backward light cone. And if I have an extended distribution of things, then I have to sum up all of those things that happen at all the different x primes. Everything that crosses my backward light cone, I see to me. As we know, in astronomy, we learn about the past by looking farther away, right? That's what's happening here. So everything that's on my backward light cone will get to me at this point in time. Awesome. All right. So, good. Now, this is the general solution, and it's the solution in the Lorentz gauge. So now, what we're interested in the same way that we did for statics, we're often interested in sources that are localized in space. And we might be looking at what the fields are, what the radiation is when I'm far away from that source. And so the way we do that is we do a multipole expansion. Yeah, Donald.
Would localize in time just be that blip you were talking about?
Well, we're gonna talk about the time in a moment. Let me proceed. So we're gonna think about the following situation. Let's say we have some charge and current, some moving charges that are moving some arbitrary way. Okay? I choose some arbitrary origin, anywhere I like, and I want to know what is the electric and magnetic field as a function of position and time, given the sources. Okay? Now, we're going to look at this we're going to parameterize this with some position for every and as before, we choose script dr to be x minus x prime. Okay. So we want to consider what the fields are for these sources under a particular constraint, okay? So we want to look at the multipole expansion. We're going to say that this thing is confined to some region of size d, okay? It might be there's an antenna and the antenna has some extent and the current is flowing back and forth, or maybe it's an atom and we're causing oscillation of the orbitals in the atom, okay? So there's some size, and as before, we're going to look at the situation where the distance from the origin to me is much, much bigger than d. So that's the far away constraint. But we're going to make another constraint, and this is about time. So I'm looking at this in the far away. And moreover, I'm going to assume that this is that this is non-relativistic. Okay? And so in particular, we're going to think about the situation. This is two conditions that we're going to look for that we can make this expansion. One is that we're far away, and the other is that the time scale over which the charges change, I'll explain that in a moment, is much, much bigger than the time it takes light to transit, give me a moment, across the sample, okay? So t here is the time scale in which rho and or j change. For example, we have an oscillating source. Then t, we would say, potentially would be equal to the period of oscillation. Okay, that's an example. And what we're saying in this case is that that period is much bigger. This thing oscillates, the time it takes it to oscillate is much longer than the time it takes light to travel across the source. That's saying something about the retarded time difference from this point of the source to that point of the source. That retarded time is much, much smaller, right? It's a tiny difference. There's not a lot of difference in the retarded times across the sample. Yes?
So this is almost the same as multiple expansions we did before, except now we're saying that our charge and current densities can vary in time.
That's correct.
Okay.
So in statics, we looked at this condition. Now we're, in addition, saying something more than these is small compared to R, we're saying also that D is much smaller than C times T. Okay? And we can write this as 2, for example, for this particular case, this would be 2 pi times C over omega. If we're at the case of we're being oscillated, okay? And what's C over omega? K. So omega. For the wave. So this is saying, in addition to us being far away, the fact that this is moving sufficiently slowly is saying that whatever wavelength is emitted is huge compared to the size of the sample. Okay, that's another condition that we're having for the multipole expansion. So let's just begin that, and we'll. So we have the exact expression. And again, T retarded is a function of XX prime and T for the potential. Okay? Now we want to make the multipole expansion for that under these conditions. So we remember our multipole expansion that we had. Well, let me remind us of the following thing. So x minus x prime is the square root of r squared minus 2 x dot x prime plus r prime squared, where r is the magnitude of x and r prime is the magnitude of x prime, right? Mm-hmm.
So we have lambda is massive compared to the size of our source. Does that mean we can get some interesting diffraction effects given the appropriate size sources?
The diffraction is about scattering. It's
Right.
not radiate. It's order of magnitude. We'll get there.
I was thinking like
Yeah.
some cavity.
Yeah. No, this is really the fact that it's just saying something about whatever the charges are doing, they're moving in such a way that the retarded time difference across the sample is small compared, to the time over which the charges change. Okay, that says something about the wavelength, but it's not really saying something about diffraction. That's really about. But I want to finish this. Okay, we need to continue. We won't get it. So, we meet the multipole expansion by saying that R is big compared to D, which means they're big compared to every R prime. And so when we did that, we made that by doing a Taylor series expansion. We factor out R, we write this as 1 over 1 minus 2 x dot x, or I can write it as R hat dot x prime over R plus R prime over R squared to the factor 1/2. Okay, where R hat is the x vector over its magnitude. Okay, so let's just factor it out. And this was approximately equal to 1 minus So from that, we saw that this is approximately equal to 1 over r times 1 over that, which is 1 plus r hat, that x over x prime over r, using, again, our friend, the binomial expansion, which is 1 over r plus r hat dot x prime over r squared, plus dot dot dot, okay? So when we are far from the source, the distance from the origin to me is approximately 1 over the distance to the origin plus a small correction that depends on r prime. This is, of course, the first order correction. You may or may not remember, this is what led us to the monopole and the dipole term in the electrostatic case. Okay? But now we have another thing, which is we have to worry about this guy. Okay? And the question is, how do we do an expansion of the retarded time under the idea that the difference of the retard, that all the differences in the retarded times is small? That's what bullet point 2 is. So the double aside here is that t retarded, which is t minus x minus x prime over c, is equal to, according to this, what we just have over here, this is equal to t minus r over c minus r hat dot x prime over c plus dot dot dot, using this expansion over here, oops, over c. So this is the, I'll call this t0. This is the retarded time from the origin. And this is the extra piece of the retarded time, which depends on where the source is. Okay? So there's a source at x prime, there's a little change in the retarded time, depending on where that is.
Don't we have conflicting assumptions when we said r is much, much greater than r prime, and we're saying that there's not a whole lot of difference in the retarded time for each bit of our distribution?
No, but there's the other question is, how big is this time? Okay. The x primes are all distributed small compared to r, but there's another point, which is that the times are all small. So I haven't made any assumption here at this point, other than r is big compared to r prime, and I made this assumption. The next assumption is going to be that this is small. This being small is bullet point 2, because every x prime is confined within D. And so this time is small compared to this time. We can follow up afterwards. So my grace period here, I will graciously give to myself. I want to write down the first terms of the multiple expansion. There's a minus sign here, there's a minus sign here, that's a plus. So, what we have then is that the potential is equal to the integral over x prime, 1 over r hat, stop it. Let's forget about that top. Let's just say this is approximately equal to this. This is the first order corrections. So this is the correction due to the fact that I'm not at the origin. This is the 1 over r correction, and this is the extra piece of retarded time. Okay? So the fact that this is small compared to T naught means I can do a Taylor series extension around T naught. Means that this is approximately equal to what it is given the retarded time from the origin plus the correction term, which is related to the time derivative. Right? That follows from the fact that f of t plus delta t is f of t plus delta t times f dot at t if delta t is much, much smaller than t. That's the Taylor series, that's the derivative, okay? So, I can now put this all together and I get the following expansion. I get that this is equal to the potential is equal to integral d cubed x So, what do we see? What's this first term? It's the monopole. So this is Q, whatever the monopole is, over R. What is this? That's the electric dipole at this time. And then we have a new term over here, which has to do with the time derivative of the dipole, which we didn't have before because we were talking about statics. Okay. What we see here is this is what was sort of the quasi-static piece. But now we have something that has to do with the changing dipole. The changing dipole leads to potential. And that changing dipole is going to lead to potential that leads to electromagnetic radiation. Okay. And so we'll conclude this next time, a little bit behind where I hope, but we'll still talk about it a little bit to give you a little bit of a preview in the homework. So we can get started on it. All right? Very good. We'll call it a day. You had it.